Let's see a problem, exercise problem of section 59 of G.F Simmons Introduction to Topology and Modern Analysis. Show that the projection of H forms a complete lattice with respect to the natural ordering as self-adjoint operator. So for that, you need to know this partial ordered set, a lattice and complete lattice. So for partial ordered set, a non-empty set which satisfies the partial order relation, that is a reflexive anti-symmetry transitive, then we can say the set P is called a partially ordered set. Similarly, lattice. A lattice is a partially ordered set in which the pair of elements has a greatest lower bound and a least upper bound. So for example, x and y are the two elements in the lattice L. Then we can denote this greatest lower bound, that is GLB, as x meet y. X meet y is minimum of xy. Similarly, least upper bound LUB is denoted by x join y, and that's equal to maximum of xy. So every non-empty subset has a greatest lower bound and least upper bound. Then we can say the subset is called the complete lattice. Again, you must know this Zorn's lemma. If P is a partial ordered set with every chain has an upper bound, then P possesses a maximum element. Let's see this. So show that the projection forms a complete lattice with respect to the natural self-adjoint operators. So for proving this, you must have these three results. Every closed subspace of a Hilbert space determine the unique projection on H, and orthogonal projection exists a closed subspace such that R of P equal to M, and PQ are projections on the closed subspace M and N if the following are equivalent, that is P less than or equal to Q, B, C part, and PQ equal to B, and these theorems are already proved. Now see the first subdivision. Every closed subspace determines a unique projection on H. So we can say that there is a 1-1 correspondence between the closed and the projections. Closed subspace of H and the projections are 1-1 correspondence since they are given that unique. So 1-1 correspondence between them. And this corresponds natural ordering as self-adjoint operator. Now M and N are the closed subspace of the projection P and Q. Then the necessary condition is given here. See the third subdivision. P and Q are the projection of the closed subspace M and N, then the condition given P less than or equal to Q. So, etc. implies M subset of N. These conditions are equivalent. So that we can say that the necessary and sufficient condition that P less than or equal to Q is that M subset of N. That is nothing but P is a projection on the closed subspace M and Q is a projection on the closed subspace N. So, P less than or equal to Q implies M subset of N. So this gives that set of all projection is a partial ordered set. So this gives the partial ordered set by the Zorn's lemma. You know that Zorn's lemma says that if every chain has a upper bound, it has the maximum element, then we can say P possesses a partial ordered set. See, this P less than or equal to Q M subset of N, this possesses a upper bound and that possesses a maximum element less than or equal to maximum element. Hence we can say the set of all projection is a partial ordered set. Now comes this. Here we need to prove that complete lattice. So just we claim one of the property, that is partially ordered set. Second property is the set should commit greatest lower bound and the least upper bound. So for that you can see Pi is a family of all projections with a corresponding range Mi. Pi is the projection with a range Mi. Then the infimum of projection is notated. Infimum is notated by meet. So meet IPI is the projection with range meet IMI. See here PI projection with range MI. So infimum of projection is notated as meet IMI with the range meet IMI. Similarly, supremum of projection is notated as join IPI and with the range is join IMI. Hence, the set of all projections on H is a partial ordered set with the property that, so already we found out partial ordered set, with now we get the property that the family Pi of projection, there exists a greatest projection meet Pi smaller than each one of them. greatest projection smaller than each one of them. See here, greatest lower bound is notated as at mid y equal to minimum. Greatest lower bound is the minimum of. Similarly here, greatest projection infimum of PI is the smaller, that is minimum. And there exists a smaller projection, joint PI is greater than. So least upper bound, that is notated here as mid-I PI, and that is the maximum of. So smallest implies greater than each of them. So that two property we got. One is partially ordered set. The second one is the greatest lower bound and least upper bound. So that we can say the projection form a complete lattice with respect to the natural ordering, a self-adjoint operator. Thank you.